Hi everyone. In this lesson, we are going to study about the second part of electrophilic aromatic substitution. In content, we will cover orientation in other ring system, qualitative treatment of reactivity in substrate and electrophile, effect of leaving group, amination, and sulfonylation. In the last lesson, we had study about the orientation and reactivity of benzene ring. Here we will discuss the orientation in other ring system. As you know, orientation means if a group already present on the benzene ring, then the position occupied by the new incoming group is decided by the substituent present on the ring. In fused ring systems, the positions are not equivalent, and there is usually a preferred orientation, even in the unsubstituted hydrocarbon. Now see the reaction. Here in naphthalene, the alpha position is the preferred site of attack. Because, when the electrophile attack the alpha position of naphthalene, the intermediate formed after the attack at alpha position is stabilized by two resonating structure, retaining one benzene ring. While only one such structure can be drawn, in case of attack at beta position. It is also observed that rate of substitution at the naphthalene nucleus is more than that at benzene nucleus. Because of the more extensive delocalization of charges in the corresponding aranium ions, naphthalene, anthracene, phenanthrene, and other fused polycyclic aromatic hydrocarbons are more reactive than benzene, and substitution is faster at both the alpha and beta positions. It is generally observed that, with increase in number of ring system, the rate of substitution increases. Heterocyclic compounds have non-equivalent positions, and orientation in their electrophilic substitution can be explained based on stability of intermediate formed by the attack of an electrophile. In 5-membered heterocyclic compound, 2 or 5 position are more preferred position for electrophilic substitution. Now you can see here, when pyrrole undergo electrophilic substitution, at position 2, we are getting 3 resonating structure, but when pyrrole undergo electrophilic substitution, at position 3, we are getting 2 resonating structure. So, furan, thiophene, and pyrrole are mainly substituted at the position 2, and all are substituted faster than benzene. In 6-membered heterocyclic compound, 3 or 5 position are more preferred position for electrophilic substitution. For example, pyridine, which is a 6-membered ring, mainly substituted at the position 3, and all are substituted faster than benzene. Effect of leaving group. In the majority of aromatic electrophilic substitutions, the leaving group is H+. Here, in this reaction, which group, X or Y, will cleave from an aranium ion, once it has been formed, and we will obtain an idea that, which electrophilic substitutions are feasible. However, a potential leaving group can also affect a reaction in the way, by influencing the rate at which attack of the original electrophile leads to attach directly at the ipso position. Partial rate factors for electrophilic attack at a position substituted by a group other than hydrogen are called ipso partial rate factors. The following orders of leaving group ability have been suggested. Number 1. For leaving groups that depart without assistance. Increasing order of such kind of leaving group are given below. Number 2, for leaving groups that depart with assistance. Increasing order of such kind of leaving group are shown here. Next come to reactivity in substrate. The rates of electrophilic aromatic substitution are not same for a set of aromatic ring system, having different substituent at a given electrophile. One always wonder the way in which substituent modify the reactivity of the aromatic nucleus. In order to answer such questions, CO relation of reactivity have been drawn, in which relative reactivity and different aromatic substitution can be expressed by equations containing one term characteristic and another term which depends only on the reaction. The best known equation for this is the Hammett equation, which was originally deduced for the benzoic acid ionization equilibrium, and defined as log K divided by K0 is equal to Rho into sigma, where K is the rate constant for a substituted compound in a reaction series. K0 is the rate constant for the unsubstituted compound in the same reaction series. Sigma is the log K by K0 for the benzoic acid ionization equilibrium, chosen as the standard reaction series. Rho is a dependent variable, which is a measure of susceptibility of substitution effects of the reaction series. Since K depends somewhat on the temperature, and critically upon the nature of the solvent. Sigma is defined specifically for water, at 25 degrees Celsius. Also, the magnitude of the substituent effect depends upon the position of the substituents on aromatic ring. There is a difference in substituent constant for all the position, that is, para, meta, and ortho substituent. It should be noted that, by definition, Hammett substituent constant are relative to hydrogen, as a basic of comparison. The sign of sigma can tell about the relative effects of substituent, which is on the aromatic ring. If we study the cases, K by K0 is greater than 1. This implies that the substituent has increased the acidity of the benzoic acid, that means sigma is positive. Such a substituent is considered to be an electron withdrawing group, because electron density is increased at the reaction site in the product benzoate anion, and an electron withdrawing group will favor this change by withdrawing electron density away from the reaction site. Groups such as metachloro, parachloro, metanitro, paranitro, etc., which have relatively large dipole moments, oriented with the positive end, directed towards the reaction sites, are considered as electron withdrawing groups. Let us consider the next case, where K by K0 is less than 1. It implies electron donating groups are present. Groups, which tend to increase the electron density near the reaction site, and this disfavor the ionization to a negatively charged ions. This includes alkyl group at both meta and para position, para-alkazine group, and para-amino groups. The substitute constant sigma is a measure of the total polar effect exacted by substituent X on the reaction center. The reaction constant Rho is the slope of the line correlating log K with sigma value of the substituent. The sign of the slope tells whether a reaction rate is accelerated or suppressed by electron donating versus electron withdrawing substituent. Negative RO is diagnostic of the development of positive charge at the reaction center in the transition state of the rate-limited step. Positive RO is diagnostic of the development of negative charge at the reaction center in the transition state of the rate-limited step. Hammett equation gave good correlation for the effect of meta and para substituent in the aromatic ring system for many different reactions, but failed for ortho-substituted system, which are attributed to the steric effect of the ortho-substituent on the reaction center. Next is quantitative treatment of reactivity in electrophile. Not all electrophiles are equally powerful, so this can be explained by Hammett equation. This approach is completely useless for ortho-substitution, since the Hammett equation does not apply there. A modification of the Hammett approach, suggested by Brown, called the selectivity relationship. Selectivity relationship is based on the principle that reactivity of a species varies inversely with selectivity. For example, on comparing the reactivity of toluene relative to benzene in aromatic substitution, these were found to be proportional to the ratio in which toluene undergoes para and meta substitution. Now you can see here, this table tells about the relative rates for substitution in benzene as well as in toluene, and how electrophiles can be arranged in order of selectivity. Now you can see here, in bromination, chlorination, benzoylation, nitration, mercuration, and isopropylation, what are the relative rates and product distribution and their ratios. This proportionality can be expressed as log F of para-methyl is equals to B log F of para-methyl divided by F of metamethyl, where F of para-methyl and F of metamethyl are the partial rate factors for substitution at para and meta position respectively. Now by defining the selective factor, SF is equals to log F of para-methyl divided by F of metamethyl. Then former equation 1 becomes log F of para-methyl is equals to B SF. This equation is now similar to Hammett RO plus sigma plus equation. B being a parameter whose value depends on the values of sigma plus for meta and para-methyl groups. Now you can see here, log F of para-methyl is equals to sigma plus of para divided by sigma plus of para minus sigma plus of meta into SF. Log F of metamethyl is equals to sigma plus of meta divided by sigma plus of para minus sigma plus of meta into SF. SF is related to ρ plus S. SF is equals to RO plus sigma plus of para minus sigma plus of meta. The selectivity factors is a measure of selectivity of an electrophile, which is expressed by the extent to which it discriminated, either between benzene and toluene or between the meta and para position in toluene. In simple words, it states that, the more reactive is the electrophile, the less is its selectivity, towards any particular atoms, or position of the substrate. Through this relation, selectivity was considered to be related to its reactivity, and assumed not to be dominated by other factors. Thus, powerful electrophile, such that those in Friedel-Crafts alkylation reactions were considered to be electrophiles, which would be less able to distinguish between substrate and position than a weakly electrophilic reagent. Thus, electrophiles operating in reactions which have low selectivity factor SF or reaction constant sigma plus are intrinsically more reactive than the effective electrophiles in the reaction which have higher value of these parameter. Amination. Amination is the process by which an amine group is introduced into an organic molecule. Aromatic compounds can be converted to primary aromatic amines in 10 to 65% of yields by treatment with hydrozoic acid, that is, HN3, in the presence of AlCl3 or H2SO4. As shown here, when benzene react with hydrozoic acid, presence of HN3, amino group, that is NH2 group, replace the hydrogen of benzene, and aniline is formed. Sulfonylation. Diaryl sulfoxides can be prepared by the reaction of aromatic compounds with thionyl chloride in presence of triflic acid. See the first reaction. Here 2 molecules of benzene react with thionyl chloride to give diaryl sulfoxide by the removal of HCl. Diaryl sulfones can be formed by treatment of aromatic compounds with aryl sulfonyl chlorides in presence of Friedel-Crafts catalyst, that is, AlCl3. Thank you.